Defined as omega, this value represents the probability that a randomly constructed program on a universal Turing machine will eventually stop. To visualize a construction, imagine every possible string of binary code, every possible program, assigned to a position on a binary tree. Because we use a prefix-free encoding, no valid program is a prefix of another, ensuring that the total sum of these probabilities, dictated by Kraft's inequality, converges to a real number between 0 and 1. While the definition is mathematically precise, the number itself is algorithmically irreducible. You cannot compute it. If you attempt to calculate omega by simply running all possible programs and adding 2 to the negative power of the program length to the sum whenever one halts, you will never know if the remaining programs are just taking a long time or will run forever. This is the halting problem made flesh. The impossibility of computing omega is not a matter of processing power, but a fundamental limit of logic. If you possess the first n bits of Chaitin's constant, you would possess an oracle capable of solving every mathematical problem that can be encoded in n bits of code. To solve the Riemann hypothesis or the Goldbach conjecture, you would simply write a program of length L that searches for a counterexample and halts if it finds one. If L is less than n, the bits of omega tell you exactly how many programs of that length must eventually halt. You run all programs of length L simultaneously. The moment the sum of their contributions matches the probability threshold defined by your n bits, you stop. If your Riemann checker hasn't halted by that point, it is mathematically guaranteed never to halt. A single real number holds the yes or no to every theorem expressible in the language of formal logic.
This density of information results in a state of maximal entropy. Omega is algorithmically random, meaning the shortest computer program capable of generating the first n bits of the number is n bits long. There is no compression possible, no formula like the Leibniz series for pi or the Taylor series for e that can spit out its digits. In any base, the digits of omega pass every statistical test for randomness. They are distributed with perfect uniformity because any pattern or regularity would constitute a shortcut in information, which would contradict the fact that it encodes the non-computable halting behavior of all programs. It is a sequence of bits that is perfectly defined, yet contains zero redundancy. The relationship between omega and Gödel's incompleteness theorem reveals a reasonless reality at the core of arithmetic. For any formal axiomatic system, such as Zermelo-Fraenkel set theory, there exists a fixed constant k. This system can prove the value of only a finite number of bits of omega, specifically no more than k bits. Beyond that threshold, the digits of omega are independent of the axioms. Whether the k plus first bit is a 0 or a 1 is a true fact that cannot be derived from any simpler principles. It is a mathematical fact that is true for no reason at all. If you want to know that bit, you must add it as a new arbitrary axiom to your system, but even then you remain blind to the k plus second bit.
This transforms the landscape of number theory into an experimental science. If we were to look at a Diophantine equation derived from omega, a polynomial of p of k, x of 1, x of 2, up to x of n equals 0, the question of whether that equation has infinitely many solutions for a parameter k becomes equivalent to asking for the kth bit of omega. Because those bits are random and uncomputable, the solutions to these equations fluctuate with total unpredictability. There is no underlying symmetry or logic to find. You are looking at a mathematical system that has run out of logic, leaving behind only a sequence of bits that are simultaneously absolute truth and absolute noise.